Hello everyone, welcome to a new lecture of our course on processing in memory systems. Today we are going to present another real-world processing in memory architecture, the one presented by Alibaba at ISSCC this year. It's based on hybrid bonding and contains processing near memory engines for recommendation systems. Remember that we have presented already a few real-world processing in memory architectures. The first one was the HB-PNM architecture that is based on DDR4 memory, and each PIM chip is extended with several DRAM processing units or DPUs. In particular, in the current generation, there are 8 DRAM banks, and attached to each of them, one of these DPUs. We also presented one proposal from Samsung called PIM DRAM, or also called HBM-PIM. It's based on HBM2 memory, where some of the memory layers have been modified in order to incorporate some PIM units that are SIMD units of 16 lanes, and they operate on 16-bit floating point numbers. Another similar architecture that we presented as well, proposed by SK Hynix, is this accelerator in memory that is based on GDDR6 memory. As you can see on the slide, there is one processing unit connected to each memory bank. And these processing units contain multipliers and another tree, and also they have the ability to execute different activation functions based on lookup tables. Another interesting innovation in this architecture is that it includes a supplementary SRAM buffer that is called the global buffer of size 2 kilobytes that is useful to move data around between processing units and between banks. And more recently, in our last lecture, we presented another proposal from Samsung that is called AXDIM. In this case, it's a DIM-based processing in memory system that has been prototyped and tested for recommendation systems. As you see in this slide, it's a DIM. AXDIM is a DIM with a standard DIM interface and 2 ranks of memory chips and an FPGA fabric, a configurable fabric, where we can implement different types of accelerators. In particular, this work presented the accelerator for recommendation systems. We are also going to talk today as well about the recommendation systems, because that's the main target of this Alibaba 3D Logic-to-DRAM hybrid bonding with processing near memory engine. And this is the paper, as I said before, presented in ISSCC this year in February. And the motivation of this paper, as you can imagine, is the memory wall, the data movement bottleneck that we have discussed several times in this course, or over the whole course. Indeed, memory bandwidth is not enough for many machine learning workloads, and in the paper, they point to several important applications like natural language processing, recommendation systems, graph neural networks, or multitask online inference. The paper also presents an interesting processing in memory classification that reminds me the classification that we have in our book chapter that we have mentioned also several times in this course and discussed with a little bit of detail in the very first lecture of this course. According to this paper, there are different types of processing in memory systems. The first one of them is the traditional system that cannot be considered processing in memory, of course, where we place CPUs, but also GPUs and FPGAs. As you may know, GPUs and FPGAs these days are starting to replace conventional DDR memories with HBM memories that provide much higher bandwidth, and that's what the paper calls 2.5D PNM. And here we can place as well recent GPUs and also FPGAs. If we think or we talk about the processing in memory systems themselves, these HB-PNM architecture could be placed here in this 2D processing near memory, where the processing in memory capabilities are inside the memory chip itself. And also here, we can place AIM from SK Hynix. The paper considers in DRAM the proposal from Samsung like a 3D design, because it's based on HBM2 memory of course, but instead of having in FIN-DRAM or in HB and PIM, instead of having the processing elements here in the logic layer of the 3D stack, in reality, we have the processing units, we have the PIM units in some of the memory layers. That's why I'm not so, I don't agree so much with calling FIN-DRAM 3D stack based processing near memory. I think it's more something between this model here, because it's definitely based on HBM memory, but the fact that the memory layers are modified to integrate the processing unit there in the memory layers themselves reminds me more like this scheme with computation in the same chip as the memory. In this classification, we are missing something that is based on a DIM or placing the processing units near the ranks, like AXDIM. I don't think it's well represented in this classification. That's why I'm placing it somehow in here between 2D and 2.5D, even though I don't think it's any of both. And finally, the proposal from Alibaba is exactly here in this hybrid bonding-based processing near memory. And the last thing, and we haven't talked about this in this course yet in detail, because there are no, let's say, real world architectures, or at least commercially available architectures, are what in the paper they call 2D computing memory, but in this course we have called it processing using memory. And there are different proposals here. NVM-based PIM is one example of this type of processing using memory, but also DRAM-based proposals, for example, the recent in DRAM that we will present and discuss later in this course. And this is the classification in our book chapter that is available, as you know, in archive, and definitely very much recommended reading for everyone interested in processing in memory. But now let's talk about this HB-PNM architecture from Alibaba. Interesting. A special characteristic of this architecture is that it's based on a logic die and a DRAM die that are vertically bonded by a technique called hybrid bonding. As you see it in the slide, it looks something like this. We have one layer of DRAM, we have one layer of this logic die for logic processing elements. The DRAM die is composed of these DRAM cores of 1 gigabit, and in the logic die, as we will discuss, we have two main types of engines. One is called the neural engine, the other one is called the match engine, and they are targeted at different steps of the recommendation system. You can take a look at this cross-section illustration that I think it's very clear about how this chip is created. We have the logic die at the bottom, we have the DRAM die at the top, and in between we have the hybrid bonding. We are going to talk a little bit more in detail about this hybrid bonding later, but first of all, let's continue introducing the architecture, and let's also recap a little bit on recommendation systems, because they are the main target of this architecture. In recommendation systems, as you may know, there is one first step where the features of either the data in the database and the query, the data in the queries are extracted. But once we have these features, we go to the recommendation system itself that first of all performs something called coarse grain matching to select some candidates, and then classifies the more important, or ranks the more important candidates, or the more representative candidates, in the second step called fine grain ranking. These two steps are mainly executed on the match engine, the coarse grain matching on the match engine of the HB-PNM architecture, and the fine grain ranking, or at least one important step of this fine grain ranking in the neural engine, as we will see. We are going to talk in detail about this architecture, but let me very briefly remind you a few things that we talked in our last lecture about recommendation systems. As I mentioned before, in a recommendation system, we will first have the feature generation for classification, object detection, and feature extraction. This step is usually compute bound according to the paper from Alibaba. So that's why it's usually a good fit for GPUs. The second part, which in reality is the most relevant part for the recommendation system itself, is this matching and ranking, the coarse grain matching and the fine grain ranking, that both steps are characterized by Alibaba folks as memory bound. Actually, in the paper, they provide the interesting numbers. More than 89% of the application, of the latency of the application is spent on the, accessing memory, and more than 82% of the energy. These two steps are typically run on CPU. And these two steps are actually the steps that I presented and mentioned in our previous lecture, where candidate recommendations are first retrieved and then ranked. In this, first of all, candidate generation, and second, the ranking. As you may remember here, we have two different models, one filtering model in order to extract the candidates. This could correspond to the coarse grain matching, while in the second step, we have the ranking model where we rank the most, let's say, relevant, most representative candidates in the order of 10 candidates or so that are going to be presented to the users. Both filtering and ranking model are typically based on these model that we see here, where both dense and sparse features, continuous features, and categorical features are used and processed in order to, first of all, filter and then rank. This model is based on the deep learning recommendation model proposed by Facebook in 2019. And you may remember this slide as well, where we talk a little bit more about the DRAM recommendation system from Facebook. Here we see the dense features, these continuous inputs, these continuous features that are typically processed by DNN layers, like for example, multi-layer perceptron, fully connected layers, and according to the analysis in previous papers, is like computation dominated, is that compute bound step, while the sparse features for categorical inputs are processed by indexing large embedding tables. Actually, these embedding operations consist of lookup and pooling operations to the embedding tables, and they typically follow a gather reduce pattern that in different frameworks has different operators. In CAFE2, for example, are these sparse length or SLS operators that essentially perform this gather and reduction operation. These steps have been characterized, both the SLS operators and the fully connected layers of the multi-layer perceptron having characterized, the performance bottleneck having identified. One interesting observation about them, and especially about the SLS operators, is that they are very low floating point intensity, and when the batch increases, there is also higher memory footprint and higher memory intensity. And actually, as the batch increases, and also as we increase the number of parallel threads executing the SLS operators, we see that the memory bandwidth can be easily saturated. One important thing that we have to observe here is that the fully connected layers, the MLP that is used in the DNN for dense features, is characterized in most of the cases as compute bound. But also, as you can see here, for very small batches, or for small batches, it's mostly memory bound in this case, right? And that's why I believe Alibaba folks have also characterized this fine grain ranking as a memory bound operation, probably because they are using small batches or even batch one. That's something that is not clearly specified in their paper. So let's talk a little bit more in detail about these two steps. First of all, in the coarse grain matching, we use as inputs binary feature vectors with 512 dimensions. As you can see here, first thing to do is to calculate the distance between the features from the query data and the features from the data in the database. And based on these, we can already select, like, in the order of magnitude of 1,000 representative items that are the candidate recommendations. And in this particular experiment from Alibaba, they are selecting these 1,000 candidates from 40,000 items. After we have done this first coarse grain matching, we go to the fine grain ranking, or the fine grain matching, where first of all, the features are in this case are 8 bits, and they have 1024 dimensions. As you can see, these features are fed to the multi-layer perceptron of 3 layers in order for the similarity prediction. And after that, we reduce the number of candidates from 1,000 to 100 that are also ranked. As you can see, because it's also indicated here in the figure, these steps are executed on the match engine that we are going to describe next. This step is also executed in the match engine, while this one is executed on the neural engine that is like the engine that is designed for acceleration of the NLP, as we are going to see. So let's talk with a little bit more detail about this 3D logic-to-DRAM hybrid bonding. First of all, you have already seen this slide. Remember that this architecture is composed by a DRAM die and a logic die. These two are fabricated, manufactured independently. The DRAM wafer and the logic wafer are manufactured independently, and then they are rotated face down and glued in some way, bonded by using this hybrid bonding. Some important characteristic of this hybrid bonding is that it's the copper to copper direct fusion that is down at really low temperatures, below 350 degrees. And one interesting characteristic and advantage of this technique over other 3D stacking technologies is that it allows us to have way lower pitch size compared, for example, this 3 micrometer to the typical pitch size in HBM memory, 35 micrometers. And this low pitch allows us to have much higher bandwidth between the layers. And that's why you can compare this 1.32 terabytes per second to these 460 gigabytes per second in HBM2E. Here you have some photographs of the DRAM die and the logic die, where you can see the neural engine region, and you can also see the match engine region. As you can see, they both run at a relatively low frequency, 300 megahertz, but that's kind of a relatively common frequency in processing in memory architectures, as we have seen in previous lectures as well. So let's go a little bit more in detail with the architecture of this HB-PNM. First of all, the DRAM die. This DRAM die, as you can see on the slide, is composed by 6x6, by this grid of 6x6 DRAM cores of size 1 gigabit. Inside each of the DRAM cores, we have 8 banks. As you can see here, this so for this section of 2 by 2, we have these 4 DRAM cores. In each DRAM core, we have 8 banks of 128 megabits. As you see, there is also on-chip ECC, like 8 megabits per every 128 megabits, and there is also like a bus of 128 bit, the I/O per bank, as you can see. In the logic die, the corresponding, underneath these 4 blocks of DRAM, what we find is these neural engines and match engines that they can access the DRAM cores through the corresponding memory controllers and physical interface, as you can see in the figure. It's interesting to highlight here that the HB, the hybrid bonding, imposes design constraints on the location of the memory controllers and the physical interface, as you can see. So we have to, when placing the DRAM layer on the logic layer, obviously this area here should match where this other area here in the DRAM core is, right? And here is where we have the row buffer and also where we have the control for accessing rows and columns in the DRAM banks. Now in the logic die, what we can see is the match engine and the neural engine for matching and ranking in the recommendation system. Here you can see let's say a closer view of these two engines. Here on the left-hand side, we have the match engine. On the right-hand side, we have the neural engine. As you can see, both can access their own DRAM blocks via this dual mode interface and the corresponding memory controllers. There are like 8 memory controllers, probably 1 per each bank of these DRAM block, and they have direct access to their own DRAM blocks, but they can also access other DRAM blocks via the on-chip bus, as you can see on the slide. Regarding the dual mode interface, it's called dual mode because it allows the engines to either access a single channel, one of the 8 banks, or the 8 banks in lockstep in order to achieve full bandwidth. And you can see here that it's composed by several input and output FIFO queues, multiplexers, and controllers. And here you can see a closer view of this dual mode interface with the support for single channel mode and lockstep mode, and read and write counters as well to support the bars requests, and as you can see here in the control unit. So now let's take a closer look at the match engine. This match engine, as I have already mentioned, is responsible for coarse grain matching, and it's right here on this left-hand side of this figure. And here you can see a closer view of it and the different components, including the 2 DRAM cores that can be accessed with the corresponding memory controllers and the dual mode interfaces. And here one address generator, distance calculator, and this max heap top K engine. We are going to talk about them in a little bit more detail. First of all, the address generator, as you can see, it generates the address for the input query, and it has also like a mode selection for different access patterns, and this mode selection is configurable via registers, as you see here. We can select the bars length or the strike, for example. Then we also find here in this match engine this distance calculator. The distance calculator obtains the similarity between the input query and the feature vectors, and it computes Hamming distance of 2 512-bit vectors that come from the data from the feature vectors and from the query data. We perform the Hamming distance calculation using these partial pop counts as well, and one other. And after that, the distance that represents how similar or dissimilar are the query and the data, we compare it to the root of the max heap that belongs to the top K engine that we are going to describe in the next slide. Depending on how it compares, we will record this candidate as a candidate that matches or not. Let's take a look at this top K engine. It's composed by the max heap hardware block and also a data structure for 1000 nodes. These nodes are represented by an address and also the distance between the query and the feature vectors for the shortest 1000 distances. And there is this top K unit, top K engine receives a new input every 2 cycles. And in the next slide, we are going to see an example of how it operates. You can imagine the data structure as a tree, as you can see here, and the way that we are going to incorporate new nodes based on their distance is by comparing the specific value, the specific distance in the input to the values that we have stored in the tree, right? By following this procedure that we see here. So In this particular example, we receive one input, a distance equal to 20. Observe that in the very beginning, all nodes in this data structure are initialized to the maximum possible value. So first of all, what we do is comparing these 20 to the maximum value in the root of the max heap. Because it's less than this maximum, then we incorporate these 20 into this whole data structure. And now, cycle after cycle, we compare the distance to the left child. And if it's less than the left child, then we swap the left child. If not, we swap with the right child. So first comparison here, 20 is less than max, so we swap. Here again, we compare 20 to max, so we swap. At this point, we receive another input. Remember that the Top K engine receives a new input every 2 cycles. So now the input is equal to 4. Again, we compare to the root of the max heap, and then we swap as needed. So perform comparison here, we swap. At the same time, we can also perform this comparison 20 compared to this max. So we'll also have to swap, and so on and so forth. The next element that or in the next distance that the Top K engine receives is this input equal to, distance equal to. So again, we have to swap here, but also observe that at this point, we are comparing this 4 with this 20. And because 4 is less than 20, we will swap here as well. Same as in the next cycle, we are also going to swap this 2 with this 20. Now the next input is 8, and we proceed the same way. Observe that sometime later, a few cycles later, the nodes have been rearranged in this way. On the left hand side, on the left branch, let's say the left children are all the smallest values, smallest distances that we have received. On the right, we have those distances that are larger. And a few cycles later, and after receiving a few more inputs, the data structure, this tree here, will look like this more or less. Observe that here, the children on the left-hand side, we have the smallest distances, while on the right-hand side, the right children, we have the larger distances. But in the end, this data structure will contain the 1,000 shortest distances that the match engine has found. So after we have that, we have to go for the fine-grained ranking, and this is performed partially in the neural engine that is responsible for similarity prediction. Here you can see a closer view of the neural engine. Again, we have here the DRAM blocks, we have the dual mode interfaces, we have some registers, address generator, and then we have the compute units themselves. Let's talk about them. The first of them is this vector process unit. In this vector process unit, observe that there are 2 separated parts. One of them is focused on obtaining or calculating activations. It's based on lookup tables, as you can see in the figure, and it has support for GLU and also for exponent. The second unit here is for transposition. It's composed by these arrays, these 2-dimensional arrays of registers, and performs a transposition of a 16 by 16 matrix in this ping pong array. As you can see also in the figure, rows are written and then columns are read, and that's the way of performing the transposition. We write rows and then we read columns, and this way we can read the transpose matrix. The other interesting component of this neural engine is this GEM unit that is for matrix multiplication, and it's essentially a 32 by 32 fully pipelined systolic array that supports or operates on int8 values. Partial sums are accumulated in this accumulator buffer, as you can see here, and here on the left you can see the 32 by 32 systolic array. There are not many details about this systolic array in the paper. In the end, it's a very short paper of only 2 pages, but if you want to learn about systolic arrays, I can recommend you this lecture from Professor Moodley. The neural engine also has its own controller. This controller is a finite state machine of 5 states, 5 working states and 1 idle state. And as you can see, each of the working states corresponds to one instruction, whether it's a read or write to memory, or it's a transposition, activation function, and the matrix multiplication. In this slide, you can see the key feature summary and also comparison to other processing in memory architectures. Observe that the authors here are comparing to FIMDRAM, to HB-PNM. They also compare to a 2D computing memory architecture that is based on SRAM and also to an NVIDIA A100 GPU. In principle, and as I have mentioned in previous lectures as well, I don't think that it really makes sense to have this direct comparison, especially because these different architectures might have been designed for different purposes, while we have the HB-PNM PIM architecture or even the A100 GPU that are more general purpose and can support many different types of workloads. FIMDRAM, for example, is targeted at neural network inference. It essentially performs multiplications and additions, while in this work, they are focusing on recommendation systems. I think it's very good and interesting to have all these numbers here, to check them, compare them, and so on, but I don't think that it makes sense to have a direct comparison of, for example, this work, this HB-PNM architecture to FIMDRAM or HB-PNM, because they are targeted at different purposes. Well, this is the processing in memory classification. As you may remember, the classification that we have in our book chapter, we can take as a summary of the different real-world processing in memory architectures that we have covered and are covering in this course. We can talk about the similarities and differences of the current PIM systems that we have discussed. I think that there are two very clear similarities. The first of them is that all the architectures that we have presented that are already commercially available, or hopefully will be commercially available very soon, are real-world processing in memory architectures that follow a processing near memory approach. Another common characteristic of these architectures is that they are based on DRAM memory. However, there are differences among these architectures as well, even though most of them, we can say that they are nearby, like HB-PNM, FIMDRAM, AIM, or this HB-PNM that we have presented today. We also have AXDIM that is near chip, or on-DIM, or near rank, as you may prefer. It's also the different processing elements that they have. In HB-PNM, we have general purpose cores, while in the other architecture, they are more like special function units, because they have been presented, prototyped, and tested for specific applications, either neural networks or recommendation systems. Also, the computing paradigm that they follow. In HB-PNM, we see that they are fine-grained multi-threaded. They are scalar cores, while in FIMDRAM or AIM or AXDIM, they are more like SIMD processors. And also in this HB-PNM, we have seen that it incorporates this neural engine that is essentially a systolic array. Also, the different data types that they use, there are some of them that are natively integer, like HB-PNM or HB-PNM, while others are floating point, for example, FIMDRAM. But among these working on floating point values, we have FIMDRAM that supports floating point 16 bits from the IEEE 754 standard, while AIM, for example, supports this bfloat 16, or AXDIM, at least the prototype that we studied, work with 32-bit floating point values. And finally, the different types of DRAM memory. Some of them DDR4 memory or LPDDR4, like HB-PNM, but also DDR for graphics, GDDR6 in AIM, and the 3-stack memory HBM2 in FIMDRAM. And here again, our classification, out of this classification, I would say that there is only one group of processing in memory types that we have not discussed in detail yet, even though we have introduced it in the first lecture of this course. as processing using memory group. In a later lecture, we are going to talk in more detail about some interesting prototype of this processing using memory group. We are going to talk about one prototype that implements processing using memory using DRAM. We are also going to talk in detail about the SIM-DRAM framework. That is a way of exploiting bit serial computation in a SIMD manner inside the DRAM arrays. There are no real-world systems. At least there are no commercially available systems yet. The closest thing to reality was presented a couple of years ago in the Micro 2019, a little bit more than 2 years. It's this compute DRAM work that is extremely interesting because they were able to execute some processing using memory operations using off-the-shelf DRAM. In order to do so, they used an FPGA-based memory controller that is from the Safari group. By using this FPGA-based memory controller, they are able to change the timing parameters, the way that the DRAM chips are accessed, and by doing so, they were able to somehow execute row clone operations that are for copying entire rows inside the same memory subarray, one source row to one destination row, and also they were able to perform logic operations in an ambit style, as we introduced in our first lecture, and we are going to see, as I said, more in detail in a couple of later lectures. Let me very briefly show you what they do in order to do this row clone or row copy operation inside the same chip, inside the same DRAM subarray. What they do is playing with these timing parameters between the activation and the pre-charge commands. By reducing them, they are able to copy one row to another row, because at the point where the second row is activated, the value, the voltage in the bit line is still different from half VDD, either above or below half VDD. And when the second row is activated, that charge is copied, it's moved to the capacitors of the row. They were also able to perform in some of the chips bitwise AND and bitwise OR operations. In the bitwise AND, for example, what they do is like shortening all this latency between activate and pre-charge very much. And by doing so, 1/3 row is, so when they are switching from one row to another row, 1/3 row is activated because its address appears in the address bus. We are going to see in a little bit, so in more detail in a later lecture. That's why I don't want to spend so much time today, but definitely super interesting work. As you'll see, we will discuss the experimental methodology as well, where they use the FPGA with the soft NC hardware and also a Peltier plate heater in order to change the temperature of the DRAM chips. They tested like 32 DDR3 modules, around 256 DRAM chips, and they show, they explain in their paper how they perform the experiments with the different DRAM modules using soft NC. First of all, they selected a random subarray, they filled the subarray with random data, then they perform these activate, pre-charge, activate commands with given latencies of T1 and T2. They play with these latencies and see what happens in the subarray, what happens in the destination rows, if whether the copy operation really happened or whether the ambit, the logic AND or the logic OR operation really happened. And they show in their work their observations. As you see in these different figures here, they are presenting for chips from different vendors. They are presenting what are the combinations of latencies T1 and T2, where they were able to perform either row copy operations or also these logic operations as well. Not in so many chips, as you see, but these ones from SK Hynix as well were able to support these logic operations. As I said, we are going to talk in way more detail about this proposal and actually presenting one prototype that we have developed in our group. In the future, I also expect that we will see many more works combining both ideas of processing near memory and processing using memory. And actually last year, we already presented very interesting work for acceleration of graph mining algorithms in processing in memory systems with processing near memory and processing using memory. Is the CISA paper that you can find in this slide, also including a link to the paper if you want to learn and read more about this proposal. And this is all for today. We will continue next Thursday with a new lecture of our processing in memory course. There is a lot more to come. As I mentioned, processing using memory architectures, frameworks, and prototypes, but we will also describe in more detail specific case studies. For example, the sparse matrix vector multiplication, which is an important primitive for many applications. It's also like a clearly memory-bound application in processor-centric systems. We will discuss our implementations of SPMB on the PIM architecture, and we will also talk about other case studies, like, for example, neural network accelerators for the edge based on processing in memory, same as accelerators for HTAP databases. And we will finish this course discussing additional challenges that still need to be solved for the adoption of processing in memory in real-world systems. So that's all for today. I really appreciate your attention. Thank you very much. Hope to see you in future lectures as well. Bye-bye.